Hello everyone, I am PRANALI SURKAR and I am working as an assistant professor in the Department of Electronics and Communication Engineering at Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. So a warm welcome to all of you in the video lecture series of Analog CMOS IC Design. We have discussed earlier what are the course objectives and course outcomes, and also we have discussed about the syllabus, and today we are going to start our first topic, that is MOS IV characteristics. But before that, I'll give you some basic information about the MOSFET structure. So here the first unit belongs to basic MOS device physics. In this we are going to discuss about the MOS device structure, where we will discuss about NMOS, PMOS, and we'll see the structure of CMOS as well. And then we have started our we'll start our first topic, threshold voltage. Now these are the remaining topics. This MOS IV characteristics we will do in the two parts. In the first part we'll discuss about the threshold voltage, and in the second part we'll discuss about the derivation of the VI characteristics. Then these are the remaining topics that we are going to cover in the upcoming lectures one by one. So as we are discussing about the analog CMOS IC design. So MOSFET, there are two types, NMOS and PMOS, and here these are the symbols for both NMOS and PMOS. MOS basically are generally we are consider it as a 3-terminal device, but we have to consider our fourth terminal also. That fourth terminal is a body terminal, which is also called as bulk terminal or the substrate terminal. So here as if we can use these symbols in different ways. So if digital, if we are considering, we are keeping this drain, gate and source 3 terminals, and we are just here without any bubble we can recognize that it is a NMOS. Now for PMOS we are giving the bubble at the gate terminal, so this is considered to be the PMOS. After that, in analog, generally we are considering it as by giving the arrow on the source terminal. So this is the NMOS. Whenever the arrow, so how to recognize that it is a NMOS or PMOS? So if the arrow is going outward from the transistor, then it is considered to be the NMOS. Always remember that arrow will be always placed on the source terminal. So if arrow is coming inside the transistor, then it will be PMOS. So if we want to, there is no necessity that we have to show body terminal, but if you want to show, you can show like this with a dotted line. So in the middle of the drain and source. So this terminal, fourth terminal is nothing but the body terminal. So these are about the symbols of MOSFET, NMOS and PMOS. Now here it is showing simple NMOS device. So as we know that NMOS means majority charge. For N, majority charge carriers will be the electrons. So here in this simple structure, we have all the terminals which we have discussed now. So this is the gate terminal. Previously the gate was made up of only metal, but now we are constructing the gate by using polysilicon. These are the source and drain terminal, and here N plus region is there. So this plus indicates that these two regions are highly doped regions. Now this is the substrate. So whenever we are considering NMOS, its drain and source will be of N-type regions, and the substrate will be the opposite, means P-type region. So P substrate is there, which is lightly doped, and there is another diffusion of P plus, which this is nothing but the body terminal to have a good contact between the substrate and this terminal. So we will having a separate P plus over here. So this is the simple NMOS device. Now opposite to it, here it is a simple PMOS device. So as the operation is completely opposite of the opposite to the NMOS. For NMOS, drain and source will be of N-type region. So in PMOS, drain and source will be of P-type. Again, it is a highly doped regions. Then substrate will be of the opposite charge carrier, means it will be of N-type. Similarly, here also the bulk terminal will be there, which is having the N plus, so that to have a good contact. Now as we are talking about the complementary metal oxide semiconductor, so complementary means here we are combining both NMOS as well as PMOS, and which if we consider the nature of PMOS and NMOS, they are complementary in each other. Means at a one time only NMOS will be on or either PMOS will be on. So now if we consider this CMOS structure, here you can find that this PMOS is inside the N well. Now why this N well is required? For example, here just look into here. This for PMOS we need a NMOS substrate over here. So if we consider that the first primary semiconductor or substrate is our P type, then this is nothing but the N plus region. So here we can say that this completely our NMOS. But just consider that if there is no well, then what will happen? So as for PMOS, we have a P-type drain and source. So, and again the substrate is also the P, then it won't be a PMOS transistor. So for this PMOS, what our requirement is? Our requirement is it should have the NMOS, as a substrate. So to create that NMOS substrate, we need the N-type doping over here, and that will be considered as a N-type substrate, which is called as N-well. So either you can have N-well, or else if your primary substrate is N-type, then you need to create P-well for the NMOS. Also you can have the twin tub also, means NMOS and N-well as well as P-well is there in the CMOS structure. So this is all about the CMOS structure. Now let's have a look on operation. Now if the first we'll consider this, the 3D figure of this MOS device. So here you can clearly see that this is N plus means drain and source region. This is nothing but the P-type substrate. Now here you can see that this portion is nothing but the polysilicon. In short, we can call it as a poly, so which is nothing but the gate terminal. Now here this is the width of the gate, which is represented as a D. Now in here we have a insulating layer, or we can call it as a oxide. So it is nothing but the SiO2, silicon dioxide, which act as a dielectric, or we can say that it is an insulating layer. Then now here some part of the oxide layer and polysilicon is coming inside the drain and source. So this complete length is we consider as a L drawn. Now this area in between the border of the drain and source, that we need to consider as a length of the channel, or we can say length of the gate. So that is nothing but represented by L effective. So if we want to find out the L effective, then what we need to do is we have to subtract this portion, which is denoted as LD, which is nothing but the diffusion. So this we need to, from LD from this side, left hand side, and here from right hand side. So 2 times LD we have to minus from L drawn. So the formula will become L drawn minus 2 times LD. So L effective is nothing but the effective length of the gate. Then L drawn is the total length, and LD is the amount of side diffusion. Now here one more thing is there which is very important, that is Tox. So Tox is nothing but the thickness of oxide layer. So this is all about the parameters in the MOS device. Now see, we'll begin with the our main topic of MOS IV characteristics, that is the threshold voltage. Now let's consider first, here 2 diagrams are there, A and B. So in the A diagram, we have written that MOSFET driven by the gate voltage, and here in this we can see that there is a formation of depletion layer. Now consider first that before this particular diagram, if we are not giving any VG, Okay, here we have given some positive VG, but let's consider that we are not giving any VG or there is no threshold voltage. So what will happen? So in that case, when we are not providing any gate voltage, the transistor will be in the off condition, means it won't be, it will be in the turned off case. So now if for example, now we'll start begin our VG, or we can say that if VG is positive, previously we are not considering any VG, or we can say that VG is negative. So in that case, there is no activity in the transistor or the device, and the device will be turned off. But as VG becomes more positive, what will happen? So here as a P substrate, there will be holes in this region. Okay, and when we are providing a positive voltage over here, that we know that opposite charges attracts each other. Okay, but now here also positive and here also positives are there. So what they will do, they will repelled back. So whatever the positive charge, positive holes are here, they will be repelling back from this gate area. So what they will do, they will leave negative ions over here. Okay, just like here it is showing negative ions. So negative ions they leave behind, and so here the depletion layer will form. So because of the positive voltage, as these positive holes are repelling back, and here only negative ions will be there, so they will form the depletion region. Now under this condition, as there is no charge carriers are available, because till now there is no channel over here, so current will not flow. As we again increase this gate voltage, so what happen, that depletion region again get widened. So width of depletion region will increase, as well as potential at the oxide silicon interface will also be increased. Now in the other case, so this structure, when there is a depletion layer form, this structure resembles like a voltage divider. Now how it will be? So here it will be the oxide layer. So here oxide capacitance will be there, and here the capacitance of depletion layer. So when interface potential reaches sufficiently positive, now also we are keeping on increasing the VG, that is gate voltage, and when it reaches to the sufficient amount, then or a sufficient positive value, then electrons will start flowing from source to drain, and in opposite direction the conventional current will start flowing from the drain to source. Keep in mind that the electrons will flow from source to drain, and the conventional current will flow from drain to source. Now at that particular time, we can say that whenever the voltage is reaching at sufficient point, the channel is getting inverted. So here what will happen, in this D diagram you can see here, these are nothing but the electron ions, but this region is nothing but called as inversion layer. Here our channel is getting inverted, or we can say that channel is created. Now so the voltage of, or the value of VG for which this phenomenon occurs, this is called as, that voltage is called as threshold voltage, and we are denoting it by VTH. So again, if VG rises further, then again the charge in the depletion region will be same or will be constant, but the channel charge density continues to increase, and as the charge density is getting increases, our current from whatever the current is flowing in between source and drain, that also getting increased. Now in semiconductor physics, the voltage threshold voltage is depending upon certain parameters. So here in this case, VTH is depending upon this phi ms, which is nothing but the work function. So work function is nothing but what we can say is it is the energy required to pull that electrons from the material or some metal. So here this phi ms is the difference between metal as well as silicon substrate. So this is nothing but the difference between the polysilicon gate. So we can write like this. So phi ms is nothing but the phi m, which is considered as a polysilicon gate, and minus phi s. S stands for silicon substrate. So this phi ms is the work function, which is the difference between this metal and the silicon substrate. Now again, this one is again you have already studied in the physics also, that is Fermi level. So we are not going into detail, but as the threshold voltage depend on this Fermi level, so we can have the formula for this. Fermi level is Fermi level equals to kT by Q ln n sub divided by ni. So you are as you are a third year students, you are very well aware about the constant, Boltzmann constant K. Then T stands for temperature, Q is nothing but the charge, and n sub is nothing but the doping density of the substrate, and this ni we can call it as a density of electrons in undoped silicon, or we can say that it's intrinsic semiconductor. Then we have the Q dip. So this is nothing but the another parameter on which threshold voltage depends. So Q dip is nothing but the charge of the depletion layer, and our fourth parameter is Cox. Cox is nothing but the capacitor of the oxide. Then, or we can say that gate oxide capacitance per unit area. Now if we see the PN junction theory again, we have another formula that is Q depletion is equals to under root 4Q epsilon Si. Then upon this is the we are taking the mod of QF for Fermi level and n sub. So whenever the question asks on write a short note of threshold voltage of MOS characteristics, then you can write till that formula, and you have to mention that on which parameter threshold voltage depends. So this is all about the threshold voltage. As there is a big lengthy topic of MOS IV characteristics, and there is a derivation, and there we are going to form some formulas we have to derive regarding current and the voltage in three regions. First region is cutoff region, second is linear region, and third is saturation region. So all these regions derivation we are going to see in the next lecture. Till then, thank you so much.